Hello, I'm Seungheon from POSTECH, and today I present our paper of programming model for efficient inter-kernel control flow on memory mapped. Oh, how uh, uh, oh, sorry. Hello, I'm Seungheon from POSTECH, and today I present our paper of programming model for efficient inter-kernel control flow on memory mapped near data processing architecture. To address the memory bandwidth and capacity wars, CXL memory has been recently proposed. However, accessing CXL memory can incur long latency and low bandwidth, causing data movement bottleneck. To address this, near data processing in CXL memory has been proposed to utilize higher internal bandwidth. In particular, memory mapped near data processing architecture enables general purpose NDP by extending the RISC-V architecture. In the NDP kernel, like the vectorized kernel in this example, many microthreads are created and mapped to data chunks in a given memory region called microthread per region. They execute vectorized kernels with fine-grained multithreading for high parallelism. However, the M20P architecture lacks a high-level programming model. Furthermore, complex workloads with iterative and conditional kernel launches can still suffer from long host device communication latency. For instance, in CUDA, kernel launch decisions are made by the host, causing frequent host device round trips with microsecond scale latency, including software overhead. Therefore, such a host-driven control flow degrades performance in dynamic workloads. To address these, graph-based approaches like CUDA graph launch multiple kernels as a task graph. By making kernel launch decisions on the device, it effectively reduces host-device communication. However, it requires manual graph constructions, as shown in this example, substantially degrading programmability. For effective NDP programming, we require a performant and easily programmable inter-kernel control flow support. In addition, we need a unified abstraction for architectural features like sketchpad memory and microthread per region, as well as an effective way to write vectorized kernel codes. To this end, we propose device main for intuitive device-driven inter-kernel control flow. Also, we provide a unified task abstraction based on C++ class. Moreover, we extend Google's Highway SIMD library for writing vectorized NDP kernels. The resulting programming model is called Arachne, and I will explain these in detail later. The device main function enables intuitive and efficient inter-kernel control flow. It is analogous to the main function of C++, but is entirely executed on a lightweight core in the NDP controller. This plot compares performance and programmability of different approaches. Compared with host-driven control flow, we reduce host-device communication for better performance. Also, compared with graph-based control flow, we improve programmability with intuitive inter-kernel control flow expression. Furthermore, we provide a unified abstraction of NDP tasks based on the C++ class. The base class NDP task bundles elements that are shared across all tasks. In detail, it exposes host-callable runtime APIs and holds common task components like device main and microthread pool region. To declare a specific NDP task, users simply inherit from this base class and define the task-specific components like NDP kernels, sketchpad memory, and the definition of device main. This provides a unified abstraction for the features of the M20P architecture. Finally, we extend Google's Highway SIMD library for expressive vector programming. We added some methods for identifying microthread, accessing metadata chunks, and vector atomic memory operations. An NDP kernel is written in SPMD manner, single code applied for all microthreads of a kernel. As an example, this vector add kernel loads 2 vectors, adds them, and stores the results to the metadata chunk. For the evaluation, we evaluate an earlier implementation of Arachne on the M20P simulator, comparing it against the baseline host-driven control flow. For this, we chose single-source shortest path, as it has iterative and data-dependent kernel launches. Arachne achieved up to 8.3 times speedup over the baseline. The performance gain increases as the host device communication latency increases, since Arachne reduces such communication. On the other hand, the performance gain decreases as the graph size increases, since the kernel runtime becomes more dominant. In summary, existing programming models trade off programmability and performance in inter-kernel control flow. Our model, Arachne, enables effective NDP offloading through device-driven control flow with device main, class abstraction of NDP tasks, and highway extended for M20P architecture. As a result, Arachne achieved up to 8.3 times speedup for SSSP over host-driven control flow, while enabling intuitive kernel programming for M20P. As ongoing work, we plan to evaluate Arachne with additional workloads and support asynchronous kernel launches in device main. Thank you for listening.
Questions? Okay, let me begin. I'm not aware of the M2 NDP architecture. Is this something different, or is this approach also applicable to GPUs, for example? So is your approach specific to M2 NDP, or can it also be applied to just GPUs?
For now, it is only applied for our the architecture M20P, but the approach is like device main. I think it can be also applied, but for GPUs, but the implementation is not ready.
Okay, it's not available. Okay, and do you see when you move the control flow from the host to the device, do you lose anything? For example, debugging ability or anything of that sort.
Debugging ability.
Because you're moving a group of kernels now.
Yes.
So it would be harder to stop after each kernel, for example.
That should be handled for the future work, I think. So.
Okay. Thank you so much. We think about it. Okay, let's thank the speaker again.